Hello everybody. We're gonna talk about the PFR and see how we can do the kinetic reactors in Aspen Plus. The example that we're gonna solve is the one that we mentioned in the previous video, which is the cracking of acetone to ketene and methane. And this is the information that we have, that it is a first order reaction with respect to acetone, and that the rate constant is calculated using this equation. And that it is a tubular adiabatic reactor, and the feed is pure acetone with flow rate of this number, and at this are the feed conditions. And we need to know what is the volume that we need to achieve 20% conversion. So the information that we have are not a lot of information, but they're like enough to start with, and we will assume some values to get started. To save some time, I have already defined these three components that we have: the acetone, ketene, and methane. And now comes the point where we need to choose the thermodynamic model. And to do this, I would prefer to go and use the method assistant. And by opening the method assistant, again, as we do every time, we will answer some questions. I think, yeah, so it is either by component type and process type. So I'm gonna choose the component type, and it is not a hydrocarbon. I have here the components that I am working with are acetone and ketene and methane. So they are polar components, so I'm gonna go for chemical system. I'm working at almost 1.5 atmosphere, so it's not a high, 1.5 bars, so it's not high pressure system. So it suggests that this to use an activity coefficient model like an RTL, Wilson, or whatever. But I can just go for that, but there is something that I need to check here, and this is important to take a look at these options because they might be of interest, like in our case. So I don't have carboxylic acids, I don't have electrolyte systems, but I have non-condensable components, which is important. If you have non-condensable components such as hydrogen, carbon dioxide, nitrogen, oxygen, in our case we have methane, which is this is non-condensable component because I'm working at temperature higher than the critical temperature of methane. So I have to declare them as Henry's component, so make sure that Henry's constants are available. So the point is to define them as Henry's component. So the base method that I'm going to use is I'm going to go for activity coefficient model, and I will define the Henry component, which is methane, or I can call it any name. It doesn't have to be methane, the name that I have defined before. So it's CH4. I can define it this way. So I told him that there are Henry's component. I named them as CH4, but the software doesn't know what is the Henry component. You will find that there is this part is red, and it's telling me that there are some missing information here. So it's asking me which one of them is the Henry component. So I'm defining this as Henry component. And by doing this, it needs to update the binary interaction parameters. So I just need to go here, and it's gonna be automatically calculated. So it's important in case you have non-condensable components to make sure that you define them as non-condensables, because if you don't do that, it's gonna do like some illogical results because of the assumption that this is condensable while it's not. So this is all what I need to do here. And now we'll go to the simulation environment, and we will see what we have. I'll just maximize this window now, and then until I need the rest of the windows. So again, we will go to reactors. We have already talked about the ideal reactors, and we need to go for this guy, the plug reactor. So I'm gonna call it PFR, and I'm gonna connect one feed stream here and one product stream here. You would notice that there are some optional streams. You can put one or more than one output or more than one product, and you can put thermal fluid, which is fluid that you are using for cooling or heating. All are optional, but at the end of the day, just you need to keep in mind that you have only one inlet. You cannot put more than one feed into or connect more than one feed into the PFR. Anyway, so now before giving all the information, I just quickly go through all these tabs so that we understand what kind of information that we can provide to the system or to the block. So they are the basic specifications which are related to the temperature. It's a specific temperature or adiabatic or constant thermal fluid or whatever. It depends on your case. So we are working with an adiabatic reactor because this is what is stated here, that this is tubular adiabatic reactor. So I'm working with it as an adiabatic reactor, and this is what you're gonna start with. But you can assume that it has a specified temperature. So the temperature of the reactor is constant by somehow. So you are adding heat or removing heat so that the temperature is constant. By choosing this, you do not care much about the way you are keeping the temperature constant. In other cases, like you have a thermal fluid, then you have to connect thermal fluid streams, and you have to specify the heat transfer parameters. You can reactor with co-current thermal fluid, counter-current thermal fluid. All these options will require information that you have to provide so that you tell the software how the heat is managed in the reactor. I'm gonna again start with the adiabatic, and then I'm gonna change it later after we do some runs with the reactor. And here it asks you if this tab of a configuration is related to the main configuration of the reactor itself. So either it's multi-tubular or single tube or single tube reactor. You can choose to have more than one tubes if you want. It tells you here that it will be something between 2 and 99,999 tubes. You can assume that the diameter changes with the length of the reactor, and this is kind of not common case, and in this case you'd see that you have to define how the diameter changes with the length, but I'm not going to choose this. I'm going to assume it's single tube reactors. I don't have any specifications related to the tube dimensions, so I'm going to put any dimensions by myself. I'm going to assume it's 1.5 meters and 0.25 meter diameter. And this part, it's talking about the phase. I'm working with vapor phase because I'm working at very high temperature. It is 1035 Kelvin, which is high temperature. So I'm gonna have all my components as in the vapor phase. And now this tab is for if you have more than one product streams, then you will define the phases in each one of these streams. And we don't have we have only one product stream, so we will not go through this. For the reactions, it's the place where you will choose the reactions that will be taking place in the reactor. I'm gonna keep this because this is the core of the reactor, but I'm gonna keep it to the end. There's an option which I still don't understand till now, that if you want to assume that there are no reactions in the reactor. So the reactor in this case would be just a pipe where the feed is flowing inside and then coming out as it is. So I see no point of doing this or considering this as a non-reactive system. Anyways, so now for the pressure tab, it is related to how you calculate the pressure drop in the reactor. You can define it as you can define the pressure as at the inlet. If it says here that process stream pressure at reactor inlet, if value is greater than zero, then this is the inlet pressure. Or it is the pressure drop at inlet if the value is smaller than zero. Anyway, so it depends on what you want to do. And then the pressure drop through the reactor that you can this part is related to the pressure at the inlet. So it can be there might be some pressure losses due to the connections at the inlet of the reactor. So this is what what this part is concerned with. This part, which is the pressure drop through the reactor, is the pressure losses inside the reactor due to the flow in the tubes and through the catalyst, if there is catalyst, and so on. So you can specify the pressure drop for the thermal and the process streams, or you can calculate them using subroutine. In this case, you will have that you find that there are more options that you will go through here, or you can use the correlation depending on if you have a correlation that you know that you would use. Like the most famous equation that I personally know are Darcy and Ergen equations. Anyway, so I'll keep it as this option. For the holdup, it is related to working with two phases and having one phase dragging the other with it. So it's holding the other phase with it. In this case, you can assume that there is no slip, or you can calculate the liquid holdup. Anyway, so I'm gonna assume that there is no slip between the phases. I personally don't have any phases here. This is related to the catalyst. You can define a catalyst that is inside the reactor, and you can define the catalyst loading, the voidage, or the particle density, or whatever. Again, I don't have any information about this, so I'm not gonna go through it. The diameter, again, we mentioned this before. This is the PSD, which is the particle size distribution. If you have the catalyst particle size distribution, you can keep or define it, because it is it's gonna affect the pressure drop. So in case you need it, you can define it. Anyway, so these are the tabs that we have. The one that I am interested in is the configuration, the specifications, and the reactions, or these are the critical ones that have to be defined. Otherwise, the reactor will not work. Here you find that you need to select reaction sets that will be included in the model. I don't have any reactions defined here, and now I need to either define a new set of reaction from here, or you can go through or go to this reaction folder, and it's gonna do the same thing. So it's gonna define one reaction, and then you can choose what kind of reaction kinetics that you have. The ones that we have are the power law kinetics. And now I can go to the definition of the reaction. The reaction can be defined again by, I need to define the reaction itself, how many moles in and how many moles out, and what are the feed or the inlets, and what are the products. And the second is the kinetics of the reaction. So I'm gonna define one reaction. The way we define reaction is kind of similar to what we did before in the ideal reactors. So I'm gonna say that the acetone is the feed, the coefficient is -1. But here we have the exponent, and the exponent is the powers that we mentioned before. So it's, I think I mentioned it before somewhere here. Which is this? It's power A, power B, whatever. In our case, the reaction is said to be, it is first order with respect to acetone, so it's power 1. And the products are ketene and methane, or all have the stoichiometric coefficients of 1, and the exponents are 0 because they're not part of the order of the reaction. So this part is done. I've now defined to Aspen Plus the reaction itself. Now for the kinetics, I have to first choose that this is vapor phase. You would have here the list of reactions that you have, so you can have more than one reaction in this set, so it's totally fine. We mentioned that it's a vapor phase, and the basis is the reactor volume, or the catalyst weight, if we define the catalyst and the weight of the catalyst. The kinetic factor has to be defined according to this form, which is KT power N E power minus E over RT. Or this, but this is in case T node is not specified. The shape that we have is this, which is like this, but it is not in the same shape. So if we take exponential of the two sides, it's gonna be K equals K node multiplied by E power minus E over RT. I need, that's why I have the Excel file open here, because I need to calculate the value of K. So K It's said that 34.34. So this is the what we have as ln k. Okay, so this is ln k. So I have k is the exponential of this. So this is the number that we are gonna use. It's 8. It's a big number, but I don't care. This is what I have from the kinetics. E power 14. N equals 0, so this term will go away, and then I need to go for E over RT. So I know from this shape that this is E over R, so E over R equals 34,222. I need to calculate E, so to calculate E I have to calculate R. The units that of this term are not specified, so the value of E is gonna depend on the value of R, because R is gonna define what is the units. So I have here R as I can put it as 8.314, which is joule per mole Kelvin, and if I want to calculate E, it's gonna be E over R multiplied by R. I know that this is of the units of 1 over K, okay, because this is divided by it's I mean it is in Kelvin, I'm sorry, because this multiplied by K is gonna be dimensionless. So I'm sorry, it's 1 over K, I'm sorry. So E is gonna be E over R multiplied by R, and this is gonna be in the units of joule per mole. Okay, so this is all what I have that I need to put in here. So this is in the units of joule per mole, or it's gonna be kilojoule per kilomole, and this is 28452 28452. Yeah. So it's now right. I'm now ready to put the reaction in the reactor. So the reaction is now totally yeah, it's totally defined, and now I need to go to the setup and back to the reactions, and I'll find that R1 is here. I need just to double click or press on this button so that it goes here, and now the reaction is done. There is one problem here that is I forgot to do, which is defining the stream, the feed stream, which is the feed at 1035 Kelvin and 162 kilopascal. The flow basis here is kilogram per hour, so its mass, it is 7850, and the reaction, the feed is pure acetone, so for the mass fraction it's gonna be 1 for acetone. So everything now is done. I've defined the all the parameters that I have, the reaction, the reactor, and the feed, and what I can do now is to run the reactor. So it's now doing the calculations, and we will see what kind of results that we can get out of the reactor. By seeing the results tab, we will see that it's mentioning that the duty, we have 0 duty because we assume that it is adiabatic. The reactor temperature, the minimum is 725 and the maximum is 761, so the temperature is decreasing in the reactor because I know this is the feed temperature. I have here for the summary, we will find some more information here. It's mentioning that the reactor dimensions that I have already defined, the reactor dimension, the diameter and length. Again, it's the residence time, the product stream. Anyway, so it's not a lot of information. So the part that is interesting here is the profiles. This is the part that I love most about this reactor, that you can see the profile of anything that you want. I can have the composition profile. I can see the acetone, for instance, because this is the reactant, so it's decreasing. I can see the profile of the temperature, so I can see how the temperature changes inside the reactor, which is awesome actually, because you can see at each point of the reactor how the temperature changes, and you'd see that this is an endothermic reaction. I think for the graph that I choose the reactor length. Yeah, I should have chosen the reactor length because it's more yeah, it's more easy to understand. So it seems that the reaction still can go more, so I can play with the setup of the reactor. So I can change the reactor length to make it 2.5. I can change the diameter to be 0.5. I can make it multi-tubular and use three reactors, three tubes. So all of these are just parameters that I can simply change, and you'd see that the conversion changes a lot, and the temperature changes to be 650. So the reaction is going more, and it's absorbing more heat. For the it's not this. I need to see the composition, and now it is reactor composition of the molar composition of acetone is now 0.7, so it's almost like 30 something percent conversion. So again, we can change as many parameters as we can. One more thing that I want to test is the effect of temperature. So before I change the or see the effect of temperature, I want to quickly revise the composition for the more flow. So I have 25 moles of methane and ketene coming out of the reactor from 135 moles. So 135 moles gave me 25 moles. If I change the reactor to be specified with a specific temperature, so I'm supplying heat to compensate that heat that is being absorbed by the reaction. So I expect the reaction to go further, and here in the stream results I expect that I have more than the 25 moles coming out of the reactor. So from the mole flows I have 111 moles. So I have almost 80 something percent conversion just by keeping the temperature constant. And now I think I can, if I take a look at the profile, this is the temperature profile. Of course, it's not going to change. But if I look at the composition profile for the molar composition for all the components that I have, then I'd see that I have both are increasing because they both are overlapping because they have the same stoichiometric coefficient. So both are coming with the same number of moles. But I'm reaching almost 90% conversion. Again, if I go to the PFR setup and I increase the length to be 3 meters, I'd expect that the conversion would be more. So you can kind of play with it until you reach the conversion that you have. So in case I'm interested in finding the length that will yield 20% conversion, so I can find here the 0.2 to be something here. So I would it will be something around here 0.8, so it's gonna be like less than 1 meter. Still you can play with the parameters to find the optimum conditions, but this is how you can play with it. So the PFR is very nice unit that generates a lot of data, and I believe that it saves a lot of time, especially if you can define more than one reaction. It's going to be very difficult to do these calculations manually. So I hope it helps, and I'll see you in the next video, inshallah. Goodbye.